Hi everyone. I'm going to be doing another exercise on the polyhedra today. So this one is actually going to focus on biscribe truncated icosahedron, which basically gives us distorted hexagons and regular pentagons. So let me actually show you by first, let's actually make this into surfaces and bake it so that we can actually look at the geometry. So this is the geometry we'll be dealing with, and you can see that the hexagons are not actually regular. They're kind of truncated triangles, and we have these regular pentagons as well. So I'm going to be doing a two-way parametric modification to this shape in Grasshopper today. So before we begin, we have to first look at the amount of curves that we have. We have 32, but we need to be able to filter some of these elements. So we need to, for instance, separate the pentagons and the hexagons from each other. So in order to do it, we use the explode function, and this will give me the number of segments. One thing I noticed is that the Polyhedra tool actually, let's do list length here actually, and look at the number of elements inside of these lists. You can see that it's actually doing a pretty good job of clustering the pentagons and hexagons. So if you look at the list, at this index, we get kind of a split between hexagons and pentagons. We can actually use that index to filter, but another easier way to do this would be to look for some sort of equality to do the filtering here. So for instance, if I were to flatten the list length and look for equality, equality is basically located under mat equality operator, and this you can use it almost like a logic gate, and look for if the value inside the list length is 6 or not. So basically I'm looking if the number of segments of these polygons is actually 6 or 5, and this will give me a list of true or false. So basically I'll get true if I'm dealing with hexagons, and I'll get false if I'm dealing with pentagons. And you can see that after index 20 we actually get a separate list, and these are all the pentagons. So we can directly use this data to dispatch our initial curve list, and this will actually separate the hexagons and pentagons. It's not actually easy to see it this way, but I'm going to just do a custom preview here so that you can actually look at it in color, so that we can attach a color swatch. And let's see, let's do a swatch. So this is our color swatch. We can do white and black. I mean, this is going to look like a football, but I think it should be okay. Let's see, I'm going to hide all these surfaces, and let's see, I mean, this didn't actually work. Maybe it's because this is red, and this side we got 12, this side we got 20. Let's see why we don't get these surfaces here. They're actually there. For some reason the custom preview didn't work. Let's try it again. If I take it out, you can see the holes. So these are basically the pentagons, and these are the hexagons. So what I want to do is actually make this into a volumetric model this time. So last video I was able to cover some sort of planar modification to these elements. In this one we are going to do some sort of volumetric interpolation. So basically we can actually do this using one set of the values. For instance, let's assume that I'm going to take all the hexagons and scale them down and I want to do this a bunch of times. And since these polyhedra have a centroid, we can actually use that for the center of scaling. For instance, if I were to do scale and look for where the polyhedra is located, this is actually the centroid of the polyhedra. So I can use this as the centroid for scaling. And we can start with, let's say, just one element here, one item. So I'm going to do first list item and just grab one of the hexagons here and operate on that individually so that we can actually test our application. And if that works on this single cell, then we can actually replicate the same operation to everything else. So I'm going to be operating on this curve. What we want to do is scale it down to its center, and we want to do it at not a large amount. So let's say that we first move it down by some low amount, let's say 0.9, and then I want to do another one that is a bit more down. Let's say this is going to be 0.8. I'm actually going to decrease the threshold, and that's basically the shape that I'm going to operate on to make this into a three-dimensional form. And we can also further take the middle section here, move it out, and scale it down on its own. So what I can do is get its area to find its center and scale the mid curve towards the center. So I can actually copy this scale operation, but this time I want to get this geometry to scale, and I want to scale it around its centroid, and we can make this basically go along its plane this time. I'm going to make it 0.5 here and turn this off, and this will be the shape. These are the curves that we are going to use to model this shape actually. And one way to model these would be to actually align them in such a way that we can connect them. So this curve here is the initial curve that rests on the outer edge of the polyhedra. We first moved it inward and then scaled it down. And then we also moved it a lot closer to the center of the polyhedra. So these will be basically the profiles that we're going to connect. So I can simply do a merge function here. And what I want to do is start from the outer edge, go to the middle, and end at the bottom. And I'm going to create a loft here. And I want this loft to be, go to the options. We can also create loft options. And we don't want it to be closed. We don't want to adjust the seams. We don't want to rebuild it. We don't want to riff it. But the loft type, we don't want it to be normal. Normal just lofts it like a surface. We want actually straight connections here. So I can simply supply index 3 here, which will give me the straight parameter. And if I supply it to my loft function, you can see that this is now like a polygonal connection. So the next thing I want to do is make sure that this would work for all these items, not just one of them. So here we were able to get a list, the first item in the list, but what I want to do is replace it with this curve. But before I do that, I want to actually graph this. And grafting it automatically solves it actually, but we can get rid of this plugin here. So I'm going to connect it to my initial curve container and delete the list item. You can see that all of the hexagons are now connected fine. So we can bake them and look at their form here. So let's observe this geometry. We haven't started modeling the pentagons yet. But you can see that the hexagons, all of them are actually following the same parameters. So we can actually control how much we want to give them volume here. Like we can move them further down. We can also make them smaller or open, and we can I think we can also control how much we want to move the mid section further down. So all of these are numerical values that help us control the parameters of this this polyhedra modeling. So we are turning some of these cells into volumes or other types of shapes, and we can actually connect them using these parameters. Now I'm going to do something else to pentagons. I'm actually going to do something similar here. First, create a list item so that we operate on one individual cell here. This will be the first pentagon in this list where we filtered the data. And what I want to do for this one is just to move it outward. So I'm going to be moving this pentagon by some amount. Now we can actually do scale here again. So if I were to do scale and get the pentagon, and the center of scale will be this point here, which is my centroid. And the scale factor, we want it to be now larger than the larger than 1, because for the hexagons we actually made it go inward, but in order for it to scale up or outward, we actually move it this way. Now one problem here is that when you scale it up, you also scale up the pentagon, so it's larger in size. What if we don't want to actually use scale here, but we just want to move it perpendicular to its location? In order to do it, we can create a translation vector. Now this geometry actually has an area, so I'm going to show you how you can actually move this object parametrically using the center as an origin, and we're going to create a vector now between these 2 points, between the centroid and the origin of this curve. So I'm going to hide these so that we can see them a bit better. Now if you remember, for moving functions, if I type in move, we take in a geometry and then we supply a translation vector to it. Now this vector is actually can be defined between 2 points. For instance, from this point to this point, I can define a translation vector because they actually have they define a length or some sort of measurement of distance between them, and they also specify some sort of direction. Now this translation vector, we need to create it under the vector tab. So if you go to vector and vector tab, here there's vector 2-point function, and this is actually a way to define a vector. For instance, if I want to define a vector from the center to these outer cells, I can do it as such, and then I'm going to use vector display to visualize how this vector looks like. You can see that I have turned this information into a direction, and this could be used for translation. For instance, if I use this vector to translate this geometry rather than scaling it, I can actually get the geometry, use the translation vector, and all I'm doing now is adding this vector onto its current location and moving it in the direction of the vector. So this will allow me to move objects without scaling them up, right? So scaling not only moves it in this case, but it also increases its size. If you want to keep its size the way it is, we need to use translation vectors. So after we translate it, then maybe we can do the scaling on the translated version. For instance, if I do area, and if I want to get the area of the translated object and use this as its center of scaling and scale the translated object, now we don't need a factor that is larger than 2. We can actually restrict it to be smaller. For instance, let's say 0.5. And this time we have a base object and a top object, and we can simply merge these two, and let's connect them here and loft them. So this is basically the geometry that we can create with the pentagons. Remember that the base is actually located on the polyhedra itself. So this would be our pentagon, and I'm going to basically graft this operation here as well and see if it applies to every other pentagon. It actually does a pretty good job of doing that. You can take out the list item here, or you can simply keep it. It's totally up to you. I'm going to replace it and take it out so that we're not confused. But once you graft it, it actually applies this operation to every pentagon. And when I enable the other geometry here, you can see that now we have transformed our polyhedra into kind of like a three-dimensional star shape. And I'm going to connect the same loft function here, loft options, and output both of these geometries to a geometry container, so that when we bake it, we actually bake one set of geometries, one group. And I'm going to select everything and hide our construction so that we look at the final parametric object itself. So let's bake it to see how it looks like. So this is basically the current state it is in. Now, one thing that I'm missing here is if you look inside, we can actually do it by using a clipping plane. So let's actually look inside of this object here. So we modeled the hexagons like a volume so that you can see this, this cell here. But the pentagons are not modeled the same way. So you can see that this part of the polyhedra is actually open. So you can see it a bit better like this. So one other option is to actually use the same scaling function and get the inner pentagon to connect to it as well. So let's actually add that to our script. I'm going to go back here and let's look at the same scale function. I think it was, let's actually dissect it here. We were getting three sets of geometry. This is the base geometry for the hexagons. And we are interested in the smallest one. So the factor that we used was 0.8. So if I make a copy of this and use the same scale factor for this one, I want to scale down the hexagons here as well with the same, towards the same center. Now, I need to add this to the lofting merge function here. So basically, this curve is the middle curve, this curve is the top curve, and this curve is the base curve. So this needs to go before the base curve. So I need to add one more stream here and supply this up here. And let's look at our loft. Now you can see that the pentagons are actually connected towards the base. Now that will actually close this part of the geometry itself. So if I bake our geometry, full geometry, now let's look at how it's modeled. So if I delete this group, you can see that the pentagons are actually closing these edges here. Let's look at it in clipping plane as well. You can flip the direction of the clipping plane. And you can see that these elements, the pentagons, are actually closing these edges of the hexagons too. So that basically gives me a better topology, better closed shape. We could actually model something else here as well, but I just wanted to show you when we are actually modeling something volumetric, it's important to make sure that the volume constraints are maintained throughout your shapes or surface models. So you can see here, for instance, we used pentagons and hexagons, and the hexagons are modeled in 3 groups and pentagons are modeled the same way. So this inner thickness is consistent, but we have moved the outer element using a vector translator, and that gave me a star shape like this. And this is actually a fully parametric object. So for instance, if we were to change some of these parameters, we can get a lot of different types of cool looking shapes. For instance, let's actually turn these off again. I want to, let's say, move it a bit more inward, make the outer pieces a bit thicker, and make this factor a bit more open, and bake it. Now the same meta object, basically, the parametric relationships we were able to build, we can actually output a lot of different sets of geometries as well. So for the second one, I changed the scaling factor of this pentagon here and this hollow element here, and you can see that that's actually how it looks like. I'm going to do another one. This time we are going to keep it on the surface a bit more. Keep this maybe a lot smaller and keep the holes a lot closed as well. And when I bake this, this is now the shape that we get. So this is actually the same polyhedra shape modeled with 3 different sets of parameters. So you can see that the same relationships help us control some of the apertures and behavior of these cells, and we can control most of these aspects parametrically. Now I hope this was helpful. You can actually investigate similar topological modeling on other types of hadrons, and we're going to be working on more volumetric examples this week. So thanks for watching.